Determine the force in member AB, BD, and FE of the space truss and state if the members are in tension or compression. Determine the force in members AF, AE, and FD of the space truss and state if the members are in tension or compression. Because there is an interconnection between the members, I'm going to do both problems simultaneously. And I've already highlighted the required members in red. And I've also highlighted or drawn the height of the joint F, which we can find using sine 60 and times it by 3 feet. And we know the angle is the angle is 60 because it's an equilateral triangle. And our solution is 3 root 3 divided by 2, which is equals to 2.598. Now to begin, let's draw our free body diagram for joint A. To begin, we know that member FE is out of plane for all other members. Therefore, we know that it is going to be a zero force member. And now to solve for the remaining members, let's start by summing the forces in z-axis. We're going to have negative 500 pounds, then positive z component of force AF. The denominator for the z component is simply going to be y and z, so 1.5 squared plus 2.598 squared, which gives us 3, all equals to 0. Solving it further, we get our solution as 577.367 pounds. And since this member is positive, we know, looking at our member AF, it is in tension. Now we can sum the forces in y direction. We're going to have negative force AB, positive y component of AF. Solving for AB, we get our solution as 288.684 pounds. And since it's positive and looking at vector, we know this is in compression. Now we can draw the free body diagram of the joint F. At joint F, we have our known force AF, and it's in tension, projecting along y and z. Found it to be 577.367 pounds. Then we have our force FP, projecting along y and z. And our other force is force FE, which is projecting along all three axes. And finally, we have our force FD, which is only projecting along x-axis. To begin, we can start by summing the forces in y direction or along the y-axis. So we're going to have y component of AF, FB, and FE. And solving for this equation, we just have to solve for one of the unknowns. In my case, I'm going to solve for force FB. And we're going to left with 0.6 force FE, and then positive 577.367 pounds. And we're going to name this our equation 1. Now we can sum the forces in z direction. Again, we're going to have z component of AF, FB, and FE equals to 0. Now what we can do here is we can plug the equation 1 into our current equation. So we're going to have negative 500 pounds, then negative 0.52 FE, and then we're going to have a negative 500 pounds and a negative 0.52 FE. all equals to 0. Solving for Fe, we get our solution as 962.279 pounds. And remember, to get this exact solution, you have to keep all the digits in your calculator. And our solution is in negative for Fe. And because it's in negative, we know we have to switch our vector to get our solution for Fe to be positive. And this also means this vector tells us that Fe is in compression. But now remember, when you plug the value of Fe into equation 1 to get the value for Fp, it needs to be negative because our old equations are still assuming Fe to be in tension. So if we plug the value of Fe into Fp1, pardon me, the equation 1, we get our solution as 0. Therefore, this means our member Fp is a zero force member. Now we can sum the forces in extraction to find our solution for member Fd. I'm going to need the negative x component of force Fe. In this case, it's going to be 962.279 times the x component, which in this case is 4 divided by 5, all equals to 0. We get our solution for Fp as 769.823 pounds. And since it's positive, the vector tells us this member is in tension. Alright, now that we have all the required members except for BD, let's go to joint B and draw its free body diagram. At joint B, we have our force AB along the y-axis, and I believe it was in compression. The value for AB was 288.689. Okay, and then we have our force FB, which we found to be in compression, and it's acting along the Y and Z, and it's 769.823 pounds. Okay, after that we have force PD, which I'm going to assume is also in compression, and it's projecting along X, Y, and Z. And then we have our force BC, which is projecting along X-axis. Pardon me, I'm going to switch over the direction of the force BD because I have intuition that it'll be in tension. Okay, and then we have our external load of 500 pounds along the axis. Okay, to solve for force BD, we actually don't have to do much. We can use pretty much any vector, or I mean axis. I'm going to go with z-axis. So we're going to sum the forces in z-axis along the z-axis. We're going to have negative 500 pounds. Then we're going to have negative force FB with its z component. And then finally we have force PD, which is going to be positive with its z component, divided by, and we have xyz. Denominator as 5, all equals to 0. Pardon me, I made a mistake here, which I just realized after. At joint F, where I said force FB, it's actually force PD, and we already had the force FB, which was 0. So it's supposed to be 0 here, so this means this whole area is 0 because our force FB is a zero force member. And now when we solve for force BD, we're going to have our solution as 962.279 pounds. And since this member is positive, and looking at